Okay, this is the final video that I'm doing for the break that we have coming up for Thanksgiving and to help you get ready for when we come back the Monday after. Remember, there will be a worksheet for the first 30 minutes of class or 25, something like that, that we'll work on. It'll count for a good deal of instructor choice points, and it'll just be to kind of make us all accountable for watching the videos. Um, and it'll also help me see if you're getting what you needed to from these sections. So 5.4, we started a little bit of this on class, but I want to expand upon it and actually show you what we need you to know how to do from this section. So it's trying to remind you that every function that is one-to-one has an inverse, and exponential functions, which remember things like y equals a to the x, have an inverse, and that inverse is called a logarithm, which I just abbreviate as a log, and it is written as y equals log base a of x, which in exponential form, if you wanted to actually write it like an exponential, would be x equals a to the y. The reason we like the log format is because this actually has it solved for y, whereas this is in a different format where y is not the solved part. So essentially, the biggest thing you need to know from section 5.4 is how to convert between log and exponential form, and then how to graph a few logs. So you really should strive to become an expert in changing between the formats. So I'm going to show you, if you're going from a log to an exponential, so this is from log to exponential. We have what we call the spiral technique for this method, and not everybody calls it that. That's my name. This is still your base, so 3, the answer to a log is always an exponent, so to the fourth equals x. So 3 to the fourth equals x. And the reason we would want to do this is because then, we can solve it. 3 to the fourth is actually 81. So when you read a log, you're actually saying, when you say log 3 of x equals 48, you're saying, let me see if I can write this clearly. 3 to the fourth power equals x, that's the exponential. But when you read a log, so when I say log like this, I always say a to what power y equals x. That's kind of how you read a log question, okay? Now, if I want to go from exponential back to log, for example, let's say we wanted to do 4 to the x equals 7. Well, we would say, okay, in a log, you kind of have 3 spots to fill in. This is base, this is exponent, because the answer to a log is always the exponent of the problem, and this is what we call the argument. So the base over here that has the exponent on it is a 4. The exponent goes on the other side, which is x, and the answer to that original was 7. The reason we would change here is because if we want to know 4 to what power equals 7, if we change it to a log, we're going to learn how to teach you how to learn how to calculate this on your calculator, because your calculator only does base 10 for log, but we will show you a way around that. So eventually you could actually solve that. Okay, so this is just showing you some equivalent forms. We're just going to practice changing these to the other formats. That's the first thing. So this would be log base is 3. I always go ahead and put my equal sign. The exponent goes on the other side, and this is 243. So that would be 3 to the x equals 243. You can kind of check yourself with the spiral. This is log base is 3. Answer would be the exponent, which is negative 4. The argument is the other part, so 1 over 81. Log base is c. Exponent goes on the other side, which is p. Answer to the original goes in the argument, so that's d. Log of base is 3. Exponent's negative 2x, and the argument ends up being the p over f. and then log of the base is 0.9. The exponent is t, so that goes on the other side, and this is 1/2. Sometimes when it's a fraction, we like to put the argument in a parentheses just to clarify that. Okay, so that's just going to log form. To go to exponential, I always use the spiral technique. Just seems to be quick for students. You start with the base, you go over, grab the exponent, you go back to the argument. So 3 to the 4th equals 81. 4 to the negative 5 equals 1 over 243. V to the Q equals W. 6 to the 3rd equals the argument, so 6 to the 3rd equals 2x minus 1. In this case, this would be useful because then we could solve. 4 to the 5 minus x equals p, and a to the 3/4 equals the 343. So this is the most important thing from this whole entire section. You need to practice converting back and forth. Okay, so what else can we do with logs? Why do we care about them? First of all, some things I wanted to remind you of. In an exponential, you had a domain of all real numbers and a range that was originally, if you don't move it, from 0 to infinity. Remember, that was our horizontal asymptote. When you're doing logs, you're dealing with the inverse, so your domain has to stay 0 to infinity, and your range is negative infinity to infinity. They flip-flop. So here's some things you have to know. Anything to the 0 power is 1. So anytime your argument is 1, the answer is 0. A to the first power is itself. If the base and the argument base match, the answer is the exponent on that argument, which is a 1. Here again, a to the a, log a of a to the x. The a matches, so it's just the exponent. Some variation here, this is a when the log is the exponent, but the base still matches as an a, so that means it's just the x. So essentially, if two parts match, the answer is the other piece. Okay, so now we're going to graph some logs. The best thing I can tell you about this part is that you can do it a couple different ways. They're one-to-one functions because they have an inverse. Remember, they have the exponentials. But you do have to care about your domain of your log. So there's a couple of different ways you could graph this. You could try, once you know how to do change of base formula, which comes later, you could try to use change of base formula to use your calculator, do a table of values. You could find the inverse function and then just do the swapping of the ordered pairs. That's kind of how I do it, but I also kind of like method 3. So if you are looking at log 5 of x, if you wanted to turn this to an exponential, that would be 5 to the y equals x, because you always have to go back to the argument. So this would be one way. If you wanted to do your table of values, you would just need to pick y's. Okay? And I'll do it this way in just a second. Another thing is to realize that the inverse to this is y equals 5 to the x. So if you find this table, just swap the ordered pairs. I don't like going through all that if I don't have to, unless I already know the inverse. Like if I've already been given the inverse to graph and then they give me this immediately after it, then yeah, I would just swap my ordered pairs. This seems more intuitive to students just to pick the y's. So 5 to the negative 2 would be 1 over 5 squared, so that's 1 over 25. So notice the x's are going to look like the things we used to see when we were doing exponentials. 5 to the negative 1 would be 1 over 5. 5 to the 0 would just be 1. 5 to the 1 is 5. 5 to the 2 is 25. So we get 1/25 negative 2, 1/5 negative 1, 1 0, 5 1, and 25 2 is way off our radar, but you see enough to see that, remember how the exponent, oh, that's a little too close to the line. The exponential function, remember, was hovering on the x-axis, whereas the log function is now hovering on the the y-axis. So we actually have a vertical asymptote, and we are just reflected over that line y equals x from the original exponential. So the ordered pairs kind of just got swapped. Some of these are harder than others. Essentially, you could just do what I did a minute ago. You can say, okay, this is y equals negative log 5 of x. When you want to do the spiral technique, the only thing that can be over here is the log, the base, and the argument. You can't have this negative over. So you do need to move that over first. And then we can do our spiral technique. So 5 to the negative y equals x. So when I pick my table this time, I'm still picking y values, but anything I plug in immediately changes signs. We would have 5 to the negative 2. So that's just 5 squared, so that makes this 25. 5 to the negative 1 would just be 5. 5 to the negative 0 would just be 5 to the 0, which is 1. 5 to the negative 1 would be 1/5, and that means the other guy has to be the 1 over 25. So essentially what happens here is that this guy gets flipped upside down on the x-axis, just like you would think if there's a negative in front. So these all still uphold the regular transformations of functions that we saw in section 3.5. Still have the same vertical asymptote, just flipped upside down. And this one is just doubling all of the so this is double our y, our y values. But if you want to think of this in terms of how would I do this by converting, the first thing we would do is divide the 2 over, because you want the log to be isolated. Then you do your spiral. 5 to this power equals the argument. And so any y value that we pick is going to get cut in half. So I'm going to make sure I pick things that are divisible by 2. So maybe -4, -2, 0, 2, and 4. So notice I kind of doubled all of my y values. And so when we plug those in, this will end up being 5 to the -4 over 2, which is 5 to the -2. So that would be 1 over 25. This will be 5 to the -1, 5 to the 0, 5 to the 2 over 2 is 5 to the 1, so that's 5. And 5 to the 4 over 2 is 5 squared, which is 25. So notice this just means that our graph got stretched a little bit. And I don't have enough room to graph out to the 25. So still have the vertical asymptote, x equals 0. Okay, here's where things start to get interesting with logarithms. Anytime your argument inside is not just an x, that means your domain has shifted. Okay, so this domain is x plus 2 is greater than or equal, or excuse me, not greater than or equal to. With logs, you have to be careful. You can't equal 0 because that would make sense. You can't raise any number to a power and actually get 0 as the answer. So the domain of this is actually bigger than -2. When we do our table, though, we're going to do it in terms of y. It's just important to see this because it'll make sense when we graph it. So this is log 5 of x plus 2. Since the log has nothing in front of it or outside of it, we can go ahead and do our spiral. So 5 to the y equals x plus 2 to solve for x, because we want this to look like we are going to be solving for x in our table. We would subtract over the 2. So my table of values, I would pick, remember my y's, I'm picking y's when we do logs. I would do -2, -1, 0, 1, and 2. 5 to the -2 minus 2 is 1 over 25 minus 2. 5 to the -1 minus 2 is 1/5 minus 2. 5 to the 0 minus 2 is 1 minus 2, which is -1. 5 to the 1 minus 2 is 5 minus 2, which is 3. And I'm running out of room. 5 to the 2 minus 2 is 25 minus 2, which is 23. Let's figure out some of these. 1/5 minus 2. We can get just decimals. That would be negative 1.8. Oh, sorry, I missed one of these. This was 3. This is negative 1. This one is 1.8. And then 1 divided by 25, and then take away the 2 is negative 1.96. This guy was also supposed to be negative. So negative 1.96, negative 2, negative 1.8, negative 1, negative 1, 0, 3, positive 1, and I can't graph the other one. But notice that this graph has not changed its shape, but it has shifted to the left too. When you have something added or subtracted inside of a log, this will shift your asymptote. Whereas in the exponentials, it was if it was added or subtracted at the end, because it had a horizontal asymptote, which is shifted either up or down. Vertical asymptotes get shifted right or left. So this now has an asymptote at x equals negative 2. So you'll note that if we have a plus 2 at the end, it's not going to change anything about the asymptote, but it will shift our graph. So for this one, if we wanted to graph it, first of all, you have to get the 2 to the other side. So you can isolate that log, raise to the power, and set it equal to the argument. When I'm picking my chart this time, I would be more careful. Because this exponent has something going on, I'm going to make sure I start with 2 in the middle of my chart so that I get a 0 out of this. Pick 2 numbers smaller and 2 numbers bigger. So 5 to the 0 minus 2 is 5 to the negative 2, so that's 1/25. Oops, sorry. I wrote my things on the wrong side. That happens sometimes. Just have to be careful. So this was 2, 1, 0, and 3, and 4. If we plugged in 0, we got negative 2, so that's 1/25. And if we do 5 to the 1 minus 2, that's 5 to the negative 1, that's 1/5. 5 to the 2 minus 2 is 5 to the 0, which is 1. 5 to the 3 minus 2 is 5 to the first. And obviously this one ends up being 5 squared, which is 25. So when we plot this, notice that these didn't really change that much, except the whole graph got shifted up too, but that doesn't affect a vertical asymptote. It only affects if you shift inside the function here. So 5, 3, and the rest I can't graph. So notice we did shift up our log, but our vertical asymptote stayed the same. Okay, I'm going to have you skip F and G because they're essentially the same things that we just did, except instead of moving to the left, you'd be moving to the right. And on this one, you'd be moving down for the graph. So just those are kind of just overkill. I would also skip this one. We don't give you any logs on a test with a fraction. So let's look at this one right here. This is y equals log 5 of negative x. It's already got an isolated log, so we can do our spiral. 5 to the y equals negative x. We would divide by the negative to get the x by itself. So we're doing, still picking y's because we're doing a log function. Negative 2, negative 1, 0, 1, and 2 should be fine because this has not been altered. But you are going to change all of your signs to negatives at the end. So we already know that this guy ends up being 1/25, so it's going to be negative 1/25, negative 1/5, negative 1, negative 5, and negative 25. So when it's inside, it does reflect it across the y-axis so that you get this general shape. It's going the other way. It still has the vertical asymptote at x equals 0. Okay, so we did a lot of that groundwork to now talk about two special types of logs. These are the ones that are on your calculator. Common log, which is base 10, and they do not write log base 10 most of the time, they just write log. And natural log is base E. We do not write log base E, we write natural log ln. That stands for that one. So you read it as ln of x, like Ellen DeGeneres, but that's how we read it. Those are just related to those special base exponentials, 10 to any power or e to any power. So the properties still hold. These are the ones that are actually the most important that I've seen for most students. If you have natural log of e, you need to know that that's 1. That's the one that pops up the most. And natural log of 1 is 0. Same thing over here. These are true. But I know that this pops up more. Okay, so let's read our directions. Change to log form. So remember that is log, base, argument, exponent. Base is 10, exponent is 4, argument is in the answer from the original, so that's 10,000. Log, base is 10. Now we would not leave this like this, sorry. We would write this as log of 10,000 equals 4. We drop the base. It's still there, it's just hidden. And then this is -3 and 0.01. So this guy would be log of 0.01 equals -3. This one's log base 10. X is the exponent, 38z is the argument. So this would just be log of 38z equals x. This one is log base e equals 4. Argument would be the d. We don't write that. We write natural log of d equals 4. And this one would be log base e. The exponent is 0.1t. The argument is the x plus 2. So this would be rewritten as natural log of x plus 2 equals 0.1t. For example, so I said a lot of this section is just practicing converting between the formats. Change to exponential form. It's wanting to change my format, sorry. This guy is just going the other way. Notice there's no base there, so that's 10. No base there, that's 10. Ln means base E, ln means base E, ln means base E. So you kind of have to think of those before you do your spiral. So this is 10 to the -8 equals x. 10 to the y minus 2 equals x. E to the 1/2 equals the argument, which is x. E to the 7 plus x equals the argument, which is z. And e to the 1.2 equals t minus 5. In this case, this would make this easy to solve with a calculator. So that's why these are so important to learn how to convert. And find the number if possible. This is to test to see if you know your properties. 8 to what power? This is how we read this. 8 to what power equals 1? Well, the only thing that makes things equal 1 would be 0. If the bases match, it's just the exponent of this guy, so that's 1. You cannot equal the 0 power, so this is undefined. Or excuse me, you can't raise something to a power and equal 0. Bases match, so the answer is just the exponent. Bases match, the answer is the other number. This guy, you don't see that right away, but you can think about 243. That would be, let's see, is that a power of 3? 3 to the 4th power? Nope. What is that? That is 81. 3 to the 5th power would be 243. So you could rewrite this as log 3 of 3 to the 5th. So that means the answer would just be 5. And I believe 128 is also a power of 2. Is it 2 to the 7th? Yes. And you'd have to play around with that. So 2 to the 7th. So the answer is just 7. Same thing for this next group. Notice that they're using logs now, so you have to understand that there's hidden bases sometimes. Notice that this also has a base 10 here, so bases match. The answer is 7. bases match because that's not defined. It has to have the base there or it's understood to be a 10. So this is -6. This is a 10 and 100,000 is a base 10. It's 10 to the, is that the 4th power? Nope. Times another one to the 5th power. So this is log of 10 to the 10 to the 5th, so the answer is 5. This one you have to be careful with. With decimals, it's usually a fraction. 10 to the 3rd is 1,000 if you reflect that upside down, so 1 divided by 1,000 is 0.001. So this is log 10 of 10 to the -3 power because it's 1 over 10 to the 3rd. Base natural log is e, so e and e match, so this is just 8. Natural log is base e, e and e match, the answer is 2/3. Okay, there was another property, I actually skipped over it when I was reading, but I'm going to write it now here. In fact, I'm actually going to take a break and stop this so that there is a 2-part split on this video. That way it'll break it into pieces.